Welcome to Chapter 7, Introduction. This is a longer chapter, so we're going to break this up into a couple of videos. This one will serve to introduce the big picture concepts. So Chapter 7, really getting into the organic reactions. Okay, we introduced reactions in Chapter 6, and here we'll talk about some specifics. We're going to talk about nucleophilic substitution, okay, but first we're going to give an intro and sort of some nomenclature and things like that. So Rx, X is fluorine, chlorine, bromine, iodine. There's 4 halogens, okay? We're not going to see much of fluorine. We'll see chlorine, bromine, and iodine. Okay? But let's draw out 4 possibilities here. This is called a methyl halide. So methyl chloride, methyl bromide, etc. R is some other group besides hydrogen. Again, the X's all have these lone pairs. They have to be there. That's a primary. We're borrowing from our understanding of primary carbons and things like that. So this carbon is attached, R is going to have a carbon in it. This carbon here in the center is attached to 1 carbon, so it's a primary. 2 carbons gives a secondary, and 3 carbons gives a tertiary. The identity, I can't stress this enough, this is the most important factor regarding the reaction coordinates. So we introduced reaction coordinate energy diagrams and the way the reaction proceeds, SN2 versus SN1. We'll talk about what those mean. This is the most important factor. So the identity of the alkyl halide. And we're talking about alkyl halides. These are all alkyl halides. What we're not talking about is vinyl halides, halides, aromatics. These are different. These 2 right here are very different. We will talk about, you will see things like this. This is what we call an allyl. We've introduced this this idea of allylic already, and then benzylic is similar. And this, the resonance and things like that. But you should recognize that these 2 are sort of special primaries, actually more reactive. Okay, so not these 2. Okay, these are sort of special types, but we'll talk a lot about primary, secondary, and tertiary. So let's talk about nomenclature briefly. 7.2. We'll talk about naming. So let's give you an example here. Let's draw it like this. Practice drawing the skeletal structure for this. And we are going to essentially treat halogens, chlorine, bromine, iodine, as almost like alkyl groups. Later on, we'll see that functional groups will have higher priority, but these are just the first substituent. Okay, so if we went from the left to the right, then we have the first substituent at carbon 3 right here, but if we go right to left, our first substituent is at carbon 2. So 1, 2, 3, 4, 5, 6, 7. Okay, going back to the naming that we learned with alkanes, we're going to name this, the parent is a heptane, and there's a chloro at the 2 position and a methyl at the 5. And then we alphabetize, so it's 2 chloro, 5 methyl heptane. Two chloro, 5 methyl, 2 heptane. C comes before M. Let's do a couple more skeletal structures. A ring. This one comes out to be 1 bromo, ethyl, cyclopentane. And the alphabetizing and the number in the ring sort of coincide. Okay, so the 1 and 2. Bromo comes before ethyl, so therefore it is number 1. Do one more here. Again, the 2 position is the earliest substituent rather than the 3 position if we went right to left. Now we have 2 methyl groups. Recall that the di doesn't count, so even though bromo comes before di, we're really saying bromo comes before methyl. So it's 2 bromo, and you need 2 5s in there. 5, 5 dimethyl heptane. 5, 5 dimethyl heptane. Recall the groups, the substituents that we went through: propyl and isopropyl, butyl, sec-butyl, isobutyl, tert-butyl, methyl, ethyl, etc. Okay, so we're going to use some common names, and you must learn these. Okay? And they're basically those. They're the straight chain substituent, one of the isomers. Okay, so methyl, ethyl, propyl, butyl, pentyl, etc. And then you got to have isopropyl, sec-butyl, isobutyl, tert-butyl. Okay, and we use these common names because it's just how we talk. Okay. So here we have, instead of this being a propane and being 2-methyl, 2-chloropropane or something like that, we say simply tert-butyl chloride, tert-butyl bromide, tert-butyl iodide. Excuse me. And then we have ethyl bromide. So you need to be able to give these common names. And I'll specify if I want common or IUPAC. I am not going to ask you IUPAC for one of these simple ones. If you can use one of those substituents, you have to use it. Okay. So, but this one, there's no for that substituent. So we name it in the IUPAC fashion. Okay. So 7.3 is physical properties. Not a whole lot to say, except that there are dipole-dipole interactions here. Those have implications. Okay, the dipoles, the reactivity of which we're going to talk about a lot. Okay, so there's dipole-dipole interactions, there's surface area considerations, and there's polarizability. Okay, so increasing polarizability as you go down the table. Let's draw that out. Fluorine, chlorine, bromine, iodine, increasing polarizability. We've introduced this term. It's just a size thing. The iodine is much bigger. It's spread out over a larger area. And this has implications for melting points and boiling points. Just go through this section, understand the basic concepts of dipoles and then polarizability. A lot of questions on physical properties, with the exception of things that are tied to reactivity. Okay, that's the more important thing. So hydrogen bonding and things like that. There's some questions that are in the back of the chapters that are relevant to that, but and on the study guide and things like that. But you know, learn the physical properties, kind of understand what's going on there. All right, so 7.4 is just interesting alkyl halides. Some of those are listed again. Some of these sections you just need to read. Okay, dichloromethane, chloroform, halothane is what they call that. It's interesting in the book. And then CF-Cl3 is freon. DDT is an interesting molecule. These are all listed in that chapter, so let's take a look at those. So 7.5, really, we begin to get into reactivity. And again, this is the big driving force for all that we're doing. So 7.5 is the polar CX bond. So let's take a look at this. We talked about electronegativity in chapter 1, and now we want to apply that. We have a polar bond. We can illustrate that with this arrow. Right, the plus charge goes towards the more electropositive element, carbon. The arrow points towards the more electronegative element, X. And use partial charges to show that. And so what we're showing here is that we have some Rx, and R is a carbon. It's the same idea as what I just drew. And we have a nucleophile. We're going to talk about different for this. We have a nucleophile that will come in here and attack. This is one mechanism called SN2. We're going to see this can be either SN2 or SN1. Okay. And you're going to form a new bond, nucleophile R, and you're going to release an X minus. Okay. It's substitution. And again, these R groups, we're talking about sp3 hybridized, okay? Not the vinyl, not the aryl. We went over at the very beginning of this lecture. Okay. So again, nucleophilic substitution reactions can be explained by Lewis acid-Lewis base interactions. It's just a broader definition. So if you look at a specific case, methyl iodide, sodium hydroxide. We're going to see more. We're just going to be kind of looking at this and looking at more and more detail, but we'll talk about the trajectory of things. But right now we're just showing a specific case. We formed a carbon-oxygen bond using arrows to explain this. And again, what are we showing? This pair of electrons here that I'm circling now is attacking the carbon, displacing the iodide. We're going to call this SN2. And we formed a new bond, carbon-oxygen bond. That was the nucleophile here. And what is our byproduct? Sodium plus, I minus. Okay. There's many more examples that we could show. We showed a negative nucleophile. We can also attack with a neutral nucleophile, the most common of which is an amine. And here the same idea. This can attack, displace the bromide, and instead of a negative nucleophile giving something neutral and giving a salt byproduct, you generate only a salt. And now this whole molecule is the organic product. There's no byproduct. Just because of the nature of nitrogen, you have 4 bonds, you got a plus charge and a Br minus. Again, these are CH3s, so you have 4 CH3s. We're just showing the one that we put on. It's an ammonium bromide is what that's called. There's lots more examples that we'll show. Let's talk about leaving group. Okay, we're showing the bromide as a leaving group for chapter 7. We're essentially we'll show some other leaving groups, but the biggest one is halogens. Okay, so chlorine, bromine, iodine are all good leaving groups. We'll see later that water is a good leaving group. We'll explain that later. Okay, NH3 is not as good of a leaving group, but the general rule is weaker base, better leaving group. So leaving group ability is corollary to weakness of basicity. Okay, so Cl minus, Br minus, I minus are all very weak bases. Right? They correspond to strong acids. They're happy with their octet, so that's why they're weak bases. They don't want to give up their electrons or share. Okay, so we have this sort of this trend, right? So decreasing basicity. NH3 versus water. Water is a weaker base than NH3, so it's a better leaving group. We'll get to water later. NH3 is not a common leaving group. Okay. And we go increasing leaving group ability. Now, the problem is these are neutral, okay? And what we're looking at is negatively charged halogens. And fluoride is actually not as good a leaving group as the rest. Okay, I'm going to leave off the lone pairs, but we're going to see that chlorine, bromine, iodine are excellent leaving groups. We're not going to try to distinguish so much, even though we have decreasing basicity and increasing polarization down the table. We're not going to try to distinguish. We're going to say these three are excellent. Okay, iodine is the best leaving group, okay, but these are all good leaving groups. And for our purposes, for chapter 7, okay, so for chapter 7, these three are all going to be leaving groups. I want you to learn a lot of other things before we do any kind of deciphering. You'll see in the book they'll talk about I minus attacking Cl, and that gets confusing. We'll mention a reaction that's pretty cool that does that, but for our purposes, these are the big three. Okay, good leaving groups. Okay, we're going to learn about the identity of the alkyl halide, and we're going to learn about leaving groups. Okay. And it's the flip side of, again, because their octets are full and they're close to the noble gases, they really wanted that electron, and now they have it, and they're happy. Okay. It's similar to the explanation of acidity. Remember we said HCl, HBr, and HI are all very strong acids. Okay. In turn, Cl, Br, and I minus are all weak. They're all weak bases. So these three plus, when we get to it in chapter 9, H2O is a good leaving group. Not OH minus, but H2O. We're going to protonate alcohols. We'll get to that. So 7.8 is nucleophilicity. So I'm kind of introducing some terms. Nucleophile. So review chapter 2. Lewis base is an electron pair donor. There's two basic categories here. It can be a Bronsted base. It can pick up a proton, attacks a proton. Then the Lewis base is being a Bronsted base. Or it can be a nucleophile. Nucleus loving. That's all that means. Basically mean it attacks an electron other than proton. And for our purposes, we talk a lot about carbon. Okay, nucleophiles attack electrophiles. Okay, they attack electrophiles, electron loving. Okay, so nucleus loving attacks electron loving. And in reality, this is not so different. We give different names to it, and that's why I like the Lewis acid, Lewis base definition. Okay, but let me give you some general trends. Stronger base equals stronger nucleophile. This is not an absolute rule, but it's a good generalization. We can look at pKa tables and think about the bases, and that's why pKa is important. Okay, so acid and base are tied together. Stronger base, stronger nucleophile. Okay, so typically negative charge sort of a dead giveaway. Okay. What we mean by stronger base, stronger nucleophile is that HO minus hydroxide is a much better base and stronger nucleophile than water. Water is a weak nucleophile, so OH minus, strong. Water still has lone pairs, but weak. Okay. So review the element effect, the inductive effect, the resonance effect, and the hybridization effect. Section 2.5. Okay. Now there can be an exception to the base nucleophile correlation. So here we're making a correlation, right? Sterics. If things get too large, then it can change things, okay? And this is where the definitions kind of become important in one way and unimportant in another way, okay? So let me illustrate. What I want you to remember is, in a sense, H plus, a proton, is the smallest E plus, okay? Electrophile. And we typically use the term electrophile for something other than a proton. Let me illustrate this point. We can have two O minuses. I'm going to fill these in, okay, with different things. Let's put this one here. This we'll give it a name that you don't need to know yet, but we'll show you this. Those are carbons. We're going to call this, let's say there's a sodium with it. I don't care right now. Sodium ethoxide. That's an ethyl group, so it's called ethoxide. This one, however, let's put two CH3s here instead of two H's. What's bigger, a CH3 or an H? Obviously, this is bigger, and so this becomes a much larger base, and typically we'll see K+. Potassium tert butoxide. T-butyl group, tert butoxide. This is a non-nucleophilic base. It doesn't act as a nucleophile. Because of the size of this, it's too big to attack a carbon. It's going to find a proton. It's only going to react as a Bronsted base. So it's a non-nucleophilic base, non-carbon attacking base. And it's a really important one. We'll mention that one a lot. It'll help us to make some predictions about reactions. Okay. So let's talk about solvent effects. 7.8c is solvent effects. We'll skip this section, but we'll address some solvent effects later. So you can read through 7.8c and mention steric effects and nucleophilicity. That was 7.8b. 7.8. You can get an intro into solvent effects, and we'll mention those later. So 7.9 is possible mechanisms. We've been hinting at this, kind of buzzing around it, and now we're going to start talking about it. 7.9 is going to deal with the possible mechanisms. So say we have a carbon X bond and we have a nucleophile. Let's draw it this way just so you can see different representations. You can put things over the arrow. And we're substituting. We've kind of established this. The leaving group is left. So how does this happen? That is the question. That's what mechanism means. What is the mechanism? The mechanics of it. So what's the reaction coordinate? What are the energies, etc.? Well, we do a lot of arrow pushing. We will do some energy diagrams and things like that. We're going to do lots and lots of arrow pushing. So at least one possibility is that you could come in here and attack carbon. Not a realistic possibility, but on paper we could draw this. you got to have a formal negative charge on carbon if you counted up your own electrons, everything like that. And then the X could leave, and that gives the product. That's fine. We can draw that, but it's one of the more ridiculous things I'll draw, and you may not think it's ridiculous, but you'll see. There should be a red flag popping up in your mind. What's the problem? You have 5 bonds to carbon. Call that a Texas carbon because everything's bigger in Texas. And so 5 bonds to carbon is a big no-no. Okay, so you can't do that. That's not a possibility. Okay, so is it possible that bond breaking is after bond making? No. So what about bond breaking before? Bond breaking before making. Is this a possibility? What do we mean by this? Same idea. We're going to substitute, leaving off some lone pairs on X. This can leave to give a carbocation. Really important intermediate. There's the lone pairs on X. And then what can happen is the nucleophile can come in here and attach, form a nucleophile carbon bond. Can this happen? We would call this heterolytic cleavage or heterolysis. Heterolysis or heterolytic cleavage. The CX bond breaks carbocation, and this would actually be very fast. We're going to go over some of these things. This is an intermediate, okay? Most important intermediate, carbocation. And then here's the formation of the nucleophile carbon. Okay, we would say the rate here is K times carbon, the alkyl halide. Unimolecular, SN1. Yes, this is a possibility. This is first order kinetics. It's unimolecular. Again, we're gonna kind of circle around these things over and over and over. Okay, so SN1, unimolecular. There's the rate equation, first order. Okay. So, and recall the reality of a carbocation. Right, we compared this to boron. There's a plus charge and an empty p orbital. It's electron deficient. It's going to be very reactive. That's why this is fast. Okay. So 1 is the order. SN1 is the order, not the number of steps. There's 2 steps in that reaction. So then that's a possibility. And then let's ask if bond breaking simultaneous with making, i.e., can they happen at the same time? Can they be concerted? The answer is, of course, yes. We've been talking about this quite a lot. We'll talk about it a lot more. Show it like this, and what we'll see is actually the nucleophile comes from the back, displaces the leaving group all in one step to form the carbon nucleophile bond. Let's draw it the way I drew it there. And we have X minus. Okay, this one is concerted. It is done in concert, in tandem. It's one step. There's no intermediate. There is a transition state. The rate equals K times the concentration of both. It's very, very important here. Okay. Second order bimolecular kinetics. SN2, substitution, nucleophilic second order. We draw the transition state for that reaction. The way we draw this, you will have to draw this. We'll give you a more concrete example, but you'll have to draw this. Partial formation of the nucleophile carbon bond, partial breaking of the carbon X bond. This is a transition state. That's what that double dagger means. We got a partial negative on the nucleophile, partial negative there. There's no partial positive on the carbon. FYI, this is the transition state. Nucleophiles attacking from the back side as the leaving group is ejected from the front side. Okay. All right, that is a sufficient introduction. We are again going to circle back around and go over these two mechanisms in much greater detail beginning in section 7.10 in our next video.